Okay, today we're going to talk about dominant frequency. It's a very important topic. It's way more important than people realize. A lot of the databases don't make it a prominent analysis point, and so you won't find a head map with dominant frequency or anything obvious. Usually, you have to dig for it in some tables somewhere. At NewMind, we find that it's a really critical component of understanding what's going on in a map. And that has been one of the more important dimensions to us since we started developing our database. So today I want to tell you why, and not only tell you, but show you some of the reasons why it's so important and so valuable when it comes to assessing people's conditions. So with that, let's get started. Okay, so let's talk a little bit about the concept of dominant frequency. A lot of people get dominant frequency confused with amplitude or magnitude when they start out. And you're talking about high and low amplitude, and then they start talking about high and low frequency. And that creates confusion because really we should talk about fast and slow frequency. And you'll hear statements like, well, they had a lot of fast wave activity or a lot of slowing in the EEG. That all pertains to dominant frequencies. So dominant frequencies different from magnitude or amplitude, which measures the amount of energy in a given frequency band. Okay? But when we look at dominant frequency, we're looking at the different frequency groups themselves and saying, are they faster or slower than normal? So let's kind of drill down into that concept and see if we can make it more clear. I think it's easier to think about all this if we think about the EEG brainwave signal as being similar to a white light, which is composed of a spectrum of light frequencies that can appear as a rainbow. I think everybody knows that. You grow up seeing that your whole life. You spray a hose in the summer at just the right angle, suddenly a rainbow appears, and kids love that. It's exciting because you're creating something that occurs in nature up in the clouds. But it's really about light going through the water and being split up into its different component bands. And of course, if you take a wheel with all the rainbow colors on it and you spin it fast enough, it turns white. And a lot of you did that in 5th or 6th grade science class, hopefully. So that's the concept we're working with. You have a raw EEG brainwave signal. It has a lot of component frequencies into it naturally. They're all in there. So we can process that just like we can send light through a prism and get all these colors. We can use a computer to break down the brainwave frequency and get a full spectrum. And it kind of happens along these lines. We have this composite brainwave that looks a lot like what you're seeing there. And let me get let's see if I can get my pointer out, because that helps. So here's our brainwave frequency. This is in the time domain, and we're just seeing the morphology of the wave as it moves up and down in amplitude, and that's your EEG trace that usually you're watching, when you're training somebody, or at least we have our software set up so that it's always right in your face, because obviously a lot of the important information about artifact and what's going on is in that trace. And but it is like white light. It's just tracing along, but within it is all these different component bands. And you can see them because you've got some big bands that might be alpha, some smaller bands that might be beta right there. And then you've got some notched bands, which may be a combination of alpha and beta combined, or theta and beta combined. So they're all embedded in here. And if you've got a real sharp eye, to look for, you can start to see it a bit. But most of us aren't that well trained, and even when you are, you can't see everything. So what we do is we put it through what's called a fast Fourier transform, which is an algorithm in the computer which shifts it from the time domain to the frequency domain. So rather than looking at it over minutes, we look at it over frequency, and that's what that term means, the frequency domain. It's a very confusing thing when you first hear about it in the field, but that's what we're really talking about. So here's one of the equations for fast Fourier. It takes several forms depending on how you're using it. And so that's the equation. And so the raw EEG, the trace, is processed through this equation, which translates it into frequency. And so here at the bottom is 0 cycles a second, then 1 cycle a second, all the way up to 30 cycles a second. So you see this raw waveform, we can suddenly see how much amplitude, okay, so on the y-axis is the amplitude, see how much amplitude is in each frequency band. So that is the frequency domain, how much power, and usually physicists like to measure things in terms of power, which is microvolts squared. In neurofeedback, in EEG, we like to see things in magnitude and amplitude, and that's what we usually work with. So here we can see the exact amplitude in each frequency band. And they often call these bands bins, 1 hertz bins. So if you hear somebody say, oh, well, I've got the 1 hertz bins, it's telling you that they're looking at the power in each frequency band. Okay. So hopefully that helps clarify that concept a little bit. Okay, so here we have a better close-up picture of that. So here's that band again from 0 to 30 hertz, and here's the spectrum, and then you can see each band, and that's called our spectral display. Now, almost every piece of equipment has a screen design. I mean, every software that comes with equipment has a screen design that gives you the spectral display. It's one of the more important things going back, to when we first started in the 80s and 90s doing this of the last century. What a lot of people don't realize is the value of this thing. You can see, for instance, if somebody's got too much high frequency beta, it'll show up in this range up here, and then you'll see subharmonics down here. At this, they show you that you've got information leaking from one filter into another through subharmonics. If you've got a big enough frequency band, you can look and see if you've got 60 hertz, you would see a big 60 hertz band. That would tell you that your sensors aren't on properly, or you might have dirty electricity. So there's a lot of valuable things about the frequency display. You can also see the distribution of the EEG. For instance, here we're seeing mostly 10 hertz, okay? Then we can see 15 hertz, and then 20. And you can see in this case that the highest power is in the 10 hertz band. And when your eyes are closed, that's how it should be. So if somebody closes their eyes and this blue band is down way low, that's not normal. This person either got a very occupied brain, or they're very stressed. Something's going on there. It could be related to blood flow in the brain to some degree. If they've got too much of the beta band is too high, that they're anxious. If this band up here in the 20 to 30 range is too high, they've got a lot of muscle tension usually. And down here we're looking at theta, down in the more this range. If that's really high with their eyes closed, they might be daydreaming or dissociating. And if the delta is really high in the green, well, they might be sleeping if it's really high. So you can see a lot of things. If somebody is not asleep and they have high delta, then it might be from an old head trauma. So you can understand why we were very excited to have spectral displays in the 90s, because we could tell so much just looking at this. This was kind of our early version of the brain map, And to some degree, when you're looking at the midline, which Martin often likes to analyze, you're seeing the spectral display in a simplified form at each location from the front to the back of the brain. And it is actually a simplified brain map. Now, it doesn't tell you what's going on at all locations, but gives you a great idea what's going on in the brain as a system. And I actually used to use this to help people decide what protocol they were going to use back in the 90s and how they were going to train. It was very effective. Now you can find this display at the bottom of your NuMind screen. If you click in the upper left-hand corner, the screen will flip over and you'll see a spectral display, and you can control it, go all the way up to the 60 cycles a second hertz, and you can see if you've got some dirty electricity or muscle tension or things like that. So very useful to know this stuff. Let's talk a little bit about frequencies and cycles and all of this. So a frequency cycle is when a brainwave swings from 0 to a positive peak. So here's the 0 line to a positive peak, then down to a negative peak, and then back up to 0 again. So that would be a cycle. Okay, and then the wavelength is peak to peak. So when you're measuring alpha or beta or theta with our software and most other software, you're measuring the peak to peak energy that's in the band. But frequency looks at cycles in a second. So if you have one cycle like this in a second, from 0 up and then down, negative, and then back, that's one cycle in a second. Now if we have 4 cycles in a second, that would be 4 cycles in a second, or 4 hertz, because hertz is kind of the standard nomenclature for frequency. And then we have 8 cycles a second, which would be 8 hertz. So 8 up and downs in a second. So that's how we're determining hertz. Again, it's different. It's how many times you're going up and down, and not how big the up and down is. Hopefully that clarifies the concept for that. So in the alpha component band, we find something very interesting, that it's made up of 8, 9, 10, 11, and 12 cycles a second. So when you look at your alpha amplitude on your software, on your trend screen, you're seeing the combined amplitude of 8 cycles, 9 cycles, 10, 11, and 12 cycles a second components of the whole alpha band. And if you use the software with the right filters, you can break down your alpha component band and see what the amplitude of each frequency is. So here we've got the biggest amplitude is between 10 and 10.5 hertz right there. And in fact, in the human brain, that is the most dominant frequency. That's the peak of the dominant frequency. Actually, dominant frequency should be between 9.5 and 10.5 hertz in the eyes closed human. I mean, that is what is the standard neurological finding is. So most people close their eyes. If they're healthy, they produce an alpha frequency that's between 9.5 and 10.5 hertz, and the power is the highest there. And that's important to remember, that the highest power in the alpha component band is between 9.5 and 10.5 hertz, because we're going to carry this over for a few slides. And you can see down in the 8, 8.5, 9, 9.5, there's not that much power down there. In most healthy people, you don't see much down there. Now, if you were meditating, you would see this peak slowly drop down here, and then here, and then here, and then here. And if you were in our Alpha Theta course, we show you with graphs and data analysis that we trick your brain in moving from here to here and keep you awake at the same time. It's a little balancing act, and a lot of people drift off. But if it's done properly with the software, we get you to float down here. Not permanently, but just back and forth. And that gets you into a meditation-like state. But when you're just sitting with your eyes closed and you're not sleepy, it stays here. However, if you started to get sleepy, the 10 hertz would go down to 9.5 to 10, and then 9 to 9.5. And then at 9, most people just drop straight off down into theta and then delta. So dominant frequency moves from theta down to delta in sleep. So this is your eyes closed dominant frequency band right here. All right. change my... So here are the different component bands. And this is delta, has a waveform like this. Theta has a waveform like this. Alpha has spindling like this. And beta has spindling. It's a little harder to see, but it's there too. So all of those component bands are in your trace, the raw EEG trace, and we break them out so that you can see them. Okay. So here's an example. I took this from BioExplorer because it's easy to see. This, I put a dominant frequency counter in here. And you'll notice that in this individual, they have normal amplitude, right, in alpha. And if we hook them up, and this is the same person, you see their dominant frequency is between 10, 10 and a half. It's actually at 10.6 cycles a second. So this is a normal person. You notice their high beta is blue. They're probably very relaxed. And so what would normally be considered high beta is lower, because most people are bracing to some degree, and when they really relax, high beta will turn blue. But notice that everything's green here, all right, for the most part. When you have a good, powerful dominant frequency around 10 hertz, on average, the rest of your frequency bands will be fairly normal. And that's a really interesting thing to keep in mind when you're looking at dominant frequency. So to make that a little bit clearer, I'll do something here that I don't often do. We're going to look at the alpha dominant frequency distribution in a clinical sample of disordered clients. So I draw from our database system, and we've got over 1 million maps in there, but we have several different data sets because some of them are in Discovery, some of them are in NewMind, some of them are in DayMed, some of them are from NeuroGuide report systems. Some of them are from our own editing tools. So we have to go in and we have to break it down, with our data dictionary and see, we got to pick everything from one group so we aren't comparing apples to oranges. So here's a sample from the NewMind software and hardware, and this is a sample of 2,662 maps, brain maps, right? And we just took the whole group, so it's everybody. Now, in this group are abnormal and normal people, because the NewMind database is plenty of people who are doing peak performance, or clinicians who are mapping themselves or their family. And by happenstance, a lot of them have fairly normal EEGs. And so, out of 1 million maps, you can get a fair amount of normal EEGs, which we do. And we can filter out through the cognitive-emotional checklist and the ISI who the normal people are. We don't do it by name. Everything is scrubbed, so we're consistent with the standards and NIH standards. And so we have the scrubbed data, and so we can look and see, who's normal, who's not, and then we can compare their EEG. Here's a good example of that huge sample. Now you'll notice here's the 9.5 to 10.5 hertz that we've been looking at and talking about. That's dominant in the healthy eyes closed person, right? But look at this clinical sample. Look at all of the frequencies here that are as high as 9.5 and higher than 10.5, right? So look at how low the healthy band is compared to the group of people, and this is going from 7 cycles to 7.5 cycles a second all the way up to 9.5. This is what you would see. This group would show up on the NewMind maps as having blue alpha in the dominant frequency. So if you were looking at the map, your alpha might be higher than normal, often it is, and it would be, probably red or yellow, and then you look down at the dominant frequency and you see it's all blue. Well, that would be because that person occupies this segment of the client population. These people have abnormal alpha frequency, they typically have abnormal EEG distributions too. So if you look at your delta, their theta, and their beta, and their high beta, you would usually see those quite a bit off too. I mean, there's exceptions, but generally speaking, that's the pattern. So here's our abnormal group of clients, and here's our more normal group of clients. But when we get up here, we start to get into some more abnormal too, because people who have too fast of an EEG up at 11 and 12 are not normal, they're abnormal. Now, they may not be a bad thing. A lot of people who have faster alpha process information faster, they're process ready, they're ready to go. So they may process information faster. On the other hand, some of these people are also hypervigilant and anxious too. So it's a double-edged sword up here. But in this range, this is where most of you should be. And if you're in this range and we looked at your EEG distribution, it would be closer to normal than if we looked at you and you were in this range. It wouldn't be normal. So you can see that's another way that we can tell how normal you might be. And a lot of people don't even know this. I mean, we're one of the only groups who know this, and we're sharing this with you because we have access to massive amounts of data, and I can edit it and process it and look at it. I do it all the time, and that's how I know what's going on in the EEG. So something to think about. Okay, given that's the case, if you have a normal distribution, so I'm going to just repeat this in a different way, here is a normal eyes open distribution. You can see here's delta, there's the frequencies down here, delta going up into beta. You see how the power declines as you go up the frequency spectrum because it's harder for the brain to produce high frequency than low frequency. It's one of the reasons. There are others. And then we have the eyes closed. We can see the delta's a little higher here. And then all of a sudden we get to theta, and a section of the theta pops up. It's almost the same as the delta. And then it goes down again in the lower frequencies at 8, 7, 8, 9 cycles a second. And then we get up to 10 hertz. Notice that it peaks up again. So that's why when your eyes are closed, your peak alpha should be somewhere about 10 cycles a second. So here it is. Here's the line, and you can see that. So if you have a normal, and this is a sample of, I think it was 10 or 12 people that were neurologically examined and thoroughly tested, and they ran it for this particular article in the Journal of Physics because they wanted to look at the power distribution in the human brain. But it's a very good example, and it's a good sample. The problem is it's only a sample of 10 people, and there might be a lot more variance in a healthy group of 10 people. And there might be things we don't know about those people that we thought we knew, like they may have had a head trauma that they didn't report or remember. So they might be a little bit off, or they may be doing pretty well, but their alpha's a little bit higher than it should be because they got a busy mind, and that's not considered a mental disorder. So even what we think is a normal sample in the normal databases is going to be tainted to some degree with stuff we've missed. That in statistics, there's inevitably error, and in investigation science, there's error. So you try to remove it. But overall, when you see this kind of distribution, you see a person with that high eyes closed alpha, that's higher than everything else, and they're at 10 cycles a second. They're going to probably be more in the normal group that we were discussing than the abnormal group. So you'll see them in this group here. Okay, so let's talk about some of these people and where they exist on the frequency spectrum and what they might tell us. So here is somebody who's got alpha dominant frequency fast. That would be a magnitude highest in the 11 to 12 hertz range. Actually 10.5 to 12, but we'll just say 11 here. Now, here would be an example of it. Here's the dominant frequency. And you'll notice that this person has normal beta, theta, and delta dominant frequency. But alpha dominant frequency here is a little fast, and you can tell because it says red is fast, green is mid, that means they're in the normative range, and blue is slow, that means they're below. They're in that 8 hertz range or even top of the 7 hertz range. So you can see right here, this person's fast. Now, what does that mean? Well, we ran this against this population against everything in the physiological checklist. And this is why it's great to have a physiological checklist. And we found a high correlation, over 70%, between fast alpha and complaints of blood sugar issues. So insulin resistance, not always, but possibly up to 70% of the time will show up as red. Now, I mean, our sample was in the thousands, so, and from clinics all over the United States, or actually all over the world. So we're pretty confident in this finding. I mean, we haven't published it. We've got lots of findings we haven't published. You know, I only have so much time, but we can apply them to the database, which is our biggest, most important interest here. There are plenty of people at universities who are starting to look at this stuff, and you'll see it coming down the road. And they even ask us for data, which we share with them. So here is that person's fast metabolics. You can see the blood sugar is starting to show up. Still not up to about 9 or 10 where it needs to be really high, but we're starting to get some nausea, craving sweets, so that's some sensitivity there. Pituitary issues are highest in this person. You see the light is yellow, so they're not sleeping well either in this group. Interesting statement. So the other group would be alpha dominant frequency slow, and those would be the people beneath 9.5 hertz, maybe in the 8 to 9 hertz range. But when you looked at our last data, you'll notice that, or you may have noticed it, goes down below 8 hertz. I mean, some of our data goes down alpha as slow as 7.8. So alpha goes down all the way to the Schumann resonance in our database. We don't see it usually going much slower than that very often. It's pretty much as slow as it typically goes, which is a very interesting concept in itself, and we'll eventually investigate that more. But here you can see this is all blue. So we got slow alpha. There's your slow alpha. They would belong in that abnormal range. And notice that the theta is red. Well, that red is because the theta band is going from 4 to 7, probably 4 to 7.5 in our database. And it picks up some of the energy from the lower 8 hertz range because filters aren't perfect, and they're tuned differently. You know, we have Butterworth filters, so we're probably picking up some of this slowed alpha. And of course, the slowed alpha shows up as diffuse elevated theta. So a lot of times when you see blue in the alpha, you're also seeing red in the theta, you're seeing very slow alpha. They're way down in the tail of the curve there in the alpha frequency distribution. So you've got alpha too fast, alpha too slow. And here's the physiology of this person. Again, interesting. They have some gastrointestinal complaints quite a bit. Not as high, but getting up there, getting up pretty high. So I would be concerned about that. And gastrointestinal issues will contribute significantly to alpha slowing because they cause an inflammatory response in the brain, which reduces serotonin, the conversion, I think it's tyrosine, serotonin pathway, reduces the serotonin, which tends to affect gastrointestinal activity. It's because the brain and the white blood cells in the brain and the gastrointestinal tract are talking to each other. So there's a good example of what might be from that. A lot of times also slow alpha can be from other issues like thyroid. So here again is an example of slow alpha, and you see the dominant frequency is all blue, theta is all red, but beta and delta are normal. So it's different from head trauma, where usually you have beta and delta, a fair amount of that area blue as well, and often theta blue too. Here you have the signature of physiology issues where alpha is blue and theta is red. And so when we look at this, we can see their thyroid is up around 12. It's even higher than the pituitary complaints. So we can tell that this person is starting to develop some T3 deficits because it's the T3 processing pathway in the brain that's related the most with ATP production and with the sodium and potassium pump output. So the brain doesn't have enough T3. It's missing a cofactor for ATP, which is resulting in lower energy production. So the brain says, well, I can't produce the beta, so I'm just going to go on standby, and that produces a lot of alpha. So you get these thyroid people often have a lot of elevated alpha that's slowed, and that's why. And, you know, that was noted in the medical literature back in the 20th century. And I mean, here's just profound confirmation. You can actually see it in the database and in your maps if you look for it. So unfortunately, we don't hear enough people in neurofeedback talking about this connection between physiology and EEG. It's kind of, people tip their hat to it, but this is a critical component of doing QEEG and relating it to people's health and how their brain is working. And so that's why we emphasize it at NewMind. Okay, so EEG frequency and myelination are also correlated too. Myelination is reflected in the peak frequency, which normalizes between the ages of 8 and 10 years. So if you have a child who's between the ages of 5 and 8, and they have slow dominant frequency, you're seeing blue in the dominant frequency, you shouldn't freak about the frequency too much, because they may just be slow at myelinating. Why? Well, they may be in a traumatic environment. The brain grows slower. They may not be getting enough nutrition. The brain grows slower. They may not be getting the right kind of nutrition, or they may have a developmental problem, a genetic problem. All of these things can contribute to slower than normal alpha dominant frequency. Now, when we look at the data in our database, and I don't have a slide for that, but I've looked at it the same way I have everything else. What you see is that in most kids in modern times, the alpha dominant frequency is up in the 9s by the time most of the kids are 7 years old. So it looks like they're myelinating faster than they did in the early 20th century. That may or may not be true because they're using analog data back then instead of digital data. They may not have been collecting sample populations the same way. They didn't have the ability like I have to go and look at thousands of maps and look at the dominant frequency. So it could be a technological issue, but the other thing is also we're more intelligent on average than we were in the 1860s, and that's been published. And part of that might be myelination and brain speed. Okay. The alpha frequency begins to decline after 60 years of age, but the shift is highly individualized. Well, once we get towards 60, if we haven't been exercising, sleeping, and getting a good diet, we're starting to develop inflammation in the brain, and that inflammation slowly eats away at the myelin sheath, and that slows down conduction velocity in the brain, and then we start to get less high frequency activity and more slowed alpha. So you'll see slow alpha more commonly in people over the age of 60. Do they have to have slow alpha? No, they don't. And a lot of research scientists are telling us this is occurring because people aren't getting enough sleep, exercise, and they're eating the SAD diet, the standard American diet, which is not good for you. The frontal lobes don't finish myelination until age 25, so you won't really get a true picture of a person's dominant frequency until they're 25 years of age. All right. Here's fast high beta bracing. So if you see high beta and you see a lot of fast dominant frequency in high beta, that's likely muscle tension. The higher frequency beta is more likely to be muscle tension. And if you went and you looked at the magnitude, you might see elevated beta, high beta right here in the same location. If they matched, you would know, okay, for sure, this is muscle tension because the high beta is red and the beta dominant frequency, high beta dominant frequency is red. So that really confirms it a lot. And here's an example of dominant frequency being very fast here, and we're seeing beta dominant frequency fast here. A lot of people with fast beta dominant frequency are processing information at an accelerated rate, and that's not uncommon in people who have anxiety, and also people who are heavily ruminating, negative rumination, a lot of negative automatic thinking and worrying. That tends to produce more fast beta. So you'll see that typically more often. Now, they could be a fast processor, but if they are, you would want to see beta and alpha asymmetry normal, and you'd say, okay, this is just a fast processor. This is not an anxious person. So obviously you have to look at dominant frequency and compare it to magnitude and symmetry to get a sense of what's going on, which is what I was just talking about. And here's a fast beta physiological profile, and you can see, being a worrier is not good. This person has a physiology score, clearly that's very high, over 100, and we have adrenals up here very high, the adrenal and cardiovascular and blood sugar. This is really typical of people with very fast beta. That's the Physio connection with them. They're producing a lot of glutamate and producing a lot of inflammation in the brain from excess glutamate. It's killing off supportive cells, and they're helping the neurons process. And the glial cells also process information themselves. This also results in sleep difficulties, which generates more inflammatory response because they're not clearing the glutamate out. So that excitotoxicity of worry is taking its toll on health. It's reducing immune system function. It's elevating cortisol and adrenal output. That suppresses immune function. So they're going to become more susceptible to viruses and bacteria and infection and inflammation. That's the cost of not sleeping enough, not exercising enough, and worrying too much, being in too stressful environments. And you see it affects the body. So if we want to do neurofeedback, we have to address those other areas if we want to be successful: sleep, diet, exercise. Okay, any good modern physician who's up on the research will tell you the same thing. Any good wellness specialist will tell you the same thing. Any good coach, life coach, will tell you the same thing. Okay, beta dominant frequency is slow. So here we can see it is a case where this person's beta is blue. That usually means slower than normal processing speed when you see that pattern. And you can see in this case even the alpha slow, which also slows down processing speed. Probably a physiological issue there. There's a case where it's just beta alone. The processing speed is slow, okay, but alpha looks pretty good. So physiology might not be as bad, but processing speed is probably slower than normal. How could you tell? Well, you could test them with any one of the NuMind computerized performance tests, see how fast they're processing information. The processing speed is in those areas. Theta dominant frequency fast, okay. Here's another example of the slowed alpha infiltrating the theta. And so if you look up at the magnitude in the brain map, you might see what looks like a lot of theta. Say, oh, his ADD's got a lot of theta. Well, and this is a problem with a lot of the old studies, is they weren't acknowledging this or looking at this. A lot of people who were doing clinical work didn't realize the implications from an electronics perspective, from more advanced electrical theory. So they were making observations without having that background. And I mean, there's obviously plenty of exceptions out there. The top people often weren't making that error, but others were, and it creates a lot of confusion. So you may see somebody who looks like what we used to say was a theta head, and they may actually just have been a slowed alpha person, which means they may have been depressed or had a food allergy or something else. Whereas if you just have this kind of theta that's dominating the skyline in magnitude, sometimes that can be reduced perfusion. So you need to look at the other component bands and the other neurometric dimensions: dominant frequency, phase, coherence, symmetry, magnitude. They all give you a little more information about what's going on in each neurometric dimension, like dominant frequency. So here's some other conditions. Many of them lack research. We have, often you'll see just slow dominant frequency delta, and that could be from myelination issues, clearly. I'm sorry, this is fast, so that wouldn't be myelination, it'd be slowed theta dominant frequency. And that's interesting. Both alpha and theta are slow. We see that in head trauma sometimes, but there's not a lot of research on this topic. So here we have slow theta and fast delta. This is from somebody who had a seizure disorder. So in this particular case, here's the absolute power of this individual with serious, grand mal seizures. And this is the resting EEG. And we're pulling this data right here from NeuroGuide. And when we're looking at the dominant frequency here and looking at what's going on, and you can see the theta dominant frequency is slow, but delta is fast. So that's obviously a signature of somebody who's probably got a fairly unstable EEG. Again, we don't have enough research on these things. But here's another seizure disorder. Interesting, right? I mean, I see this pattern quite often. Here's, again, elevated delta and theta, which you see a lot of slow wave activity in people with seizure disorder with eyes closed. They have excessive slowing, and we call this slowing because delta and theta dominate the whole spectral skyline from delta to high beta. And the dominant frequency, again, is fast and theta is slow. So to me, this is a sign of cortical instability when you see delta fast and theta slow. I wish somebody would do more research. Then we just have slow dominant frequency only, and as I jumped the gun earlier, that usually means slower conduction velocity. That would interfere with memory processing and cognitive processing in general, and would probably be more commonly found in somebody who has inflammation. This is from somebody who had a TBI, so you can see that it is consistent with that kind of condition. And then we have slow delta, fast theta. So there's these combinations that we really don't know that much about. There hasn't been much research. Here's a map of somebody with mold. I say advanced mold because they've had mold a long time. They've had it so much that they've got slowed alpha. They're depressed. And you can see this slowed alpha looks like theta. Look how high that theta is. But if we look down at dominant frequency, there's your blue, slowed alpha, and fast theta. This is more than likely mostly slowed alpha in the upper end of the 7 Hertz range. Now, we could also find out more by doing further analysis with filtering, but that's beyond most people's skill set. And our database system is not set up to do that because we're mostly just an applied database built for clinical work and not for research. So that sometimes we'll refer you to other databases if you want to do research, because they're very carefully crafted to do a lot of interesting and unusual things which you don't typically need to do clinically. And we're not interested in those particular features. Here's Parkinson's. This is delta that's elevated and theta that's elevated. Notice that's a common finding in Parkinson's, and you have the slowed alpha again. Notice they've got big beta deficiency and some alpha deficiencies. Dopamine is an important component of producing beta, and so is norepinephrine. If you don't have adequate amounts of those, you'll often have lower beta. So here is a typical slowing, Parkinson's. Now, here's another slowing, but this is dementia. This is somebody who had, these people were differentially diagnosed. There's Parkinson's, there's dementia. Not that different, although we see a lot more slowing in the dominant frequency. See all the blue there? Look at the Parkinson's. We've still got quite a bit of green in Delta and Theta. Now, if this got any more advanced, eventually the physiology gives out, you might see some slowing here. But the dementia is really going straight after the white matter, whereas the Parkinson's is more about dopamine deficits and the substantia nigra and its inability to produce dopamine in the brain. So we will get expectedly different maps. Here's TBI. Now notice in the TBI, it's blue across the whole board. Where have you seen it? We've been through all these disorders, all these other discussions. You have not seen blue across the board up to this point in the presentation. There it is. And notice there's the delta, right, is elevated. So we've got a lot of inflammation, head trauma, blue across the board. So these are two of the key features of head trauma often, is diffuse elevated delta and global slowing in the dominant frequency. Now, this doesn't all have to be perfectly blue. You can see little bits of green and red. The human brain is very complex. So you get other things in here, but you're looking for a dominance of blue, a strong theme of blue in the dominant frequency with diffuse elevated delta. And that's usually indicative of head trauma. Interestingly enough, we also have a deficit of beta, which sometimes does and sometimes doesn't show, but more often shows up than not in head trauma. Some interesting things, a little bit of slowed alpha in the back. Here's another TBI. This is regional. Notice that it's mostly in the peripheral areas here. There's your TBI right there, inflammation. And we go down here and you can see a theme of blue. Now notice that theme of blue is now contaminated with more than your typical amount that we saw in the previous one. Let's see if I can get the previous one up. There's global, really pronounced head trauma, diffuse delta with general slowing. There is more regional or local head trauma, and you can see the slowing is not as evident, but it's still there. There's a strong theme of blue. So don't be thinking black and white with the brain. Okay, so that is our presentation on dominant frequency for today. Hopefully that expanded your understanding of it and gave you some new ideas about how to look at your brain maps.